So now we discuss the going down theorem. So say we are given integral domain like this, a lies in b, with a being normal, that it is integrally closed, and b being integral over a. Then consider these prime ideals p prime contained within p. Both of these prime ideals lie within a. So p prime is contained within p, and both of these prime ideals lie within a. And let this q be a prime ideal of p. So q is a prime ideal of p such that this q lies over p. So this q intersection a is p. So if you contract this q back to a, you will get p. So a is contained within b, q is a prime ideal, and p is a prime ideal which lies below it. So you contract q back, you get p. So q intersection a is p. So our job is now to show that q actually contains another prime ideal q prime in b, such that this q prime lies over p prime right here. So if you contract this q prime back, it will go to p prime. So q prime intersection a is p prime, and notice the containment sign. Q prime is contained within q. Here p prime is contained within p. So notice that this containment is in the opposite direction compared to the going up theorem. So therefore this is called going down theorem, because notice the containment signs, they are opposite. So what should be our strategy to solve this? So we have to find this q prime. So there exists this q prime. So the first thing we should do is take this prime ideal p prime, because we have to find something lying over it. Take this prime ideal p prime and extend it in ring B. So we do the extension in ring B. So this is the extension p prime B. So this is the extension of our ideal lying here. So this will give you p prime of b. So now we have to work with this q also. So there are only two things which we can do with q. So either we can modulo out q from this prime ideal b, but that is useless, because if we modulo out q, we have to show that this contains q prime, then everything will be killed which is inside this q. So we cannot modulo out with q. So the only other operation left is localization. So we can localize like this with respect to this prime ideal q. So once we localize, we get a new ring b sub q, and then we can consider extension of p prime, or you can say this p prime, in this bigger ring p prime b sub q. So this is localized ring. So instead of this, we can consider this ring. Now if you pick up some element b in this ring and it contracts to b here, then we have to show that this b also lies in p prime. So this equality we have to show. So that is, if you contract back, you should get the same element. So suppose b lies in the contraction, then we have to show that p lies in p prime. So this is the fundamental result we have to show. But this is not that easy to show. It will require lemmas and propositions from the previous lecture. So once we are able to show that this contracts back right here, then this is the prime ideal we are looking for. So we can take its contraction back in B, and this naturally lies over P prime. So the contraction of this back in B we designate as Q prime. And you know that in localized rings there is one-to-one correspondence between prime ideals here and the prime ideals here which contain these such prime ideals. So therefore the result will hold. So let us start with B lying in P prime of PQ. So B has to be of a form of fraction. So B is y by s. So the numerator lies in P prime of P, and the denominator s lies in the multiplicatively closed set S, which is of the form ring B, and you take out the prime ideal Q. So this is just the definition of P from localization. Now let us consider this lemma here. So notice that y lies in P prime of P. So the lemma says let a prime be integral closure of a and b. So for us a is normal, so a is equal to a prime. So then the integral closure of this ideal a in b. So we are now considering the integral closure of ideal p prime. So this is ideal p prime. So integral closure of ideal p prime in b is radical of uh, p prime of a, because a prime is equal to a since we are working in a normal ring. So, and instead of ideal a, we are considering p prime. So the closure of p prime in b, that is p prime of b, is radical of p prime. Now meaning radical of p prime is just p prime, because for a prime ideal, radical of a prime ideal is just the prime ideal itself. So we have constructed the integral closure of this p prime of b as p prime which lies within a. So this y lies in this p prime of b, so therefore y is integral over p prime, because we have just constructed this integral closure. So y is integral over p prime. So we just stop here and keep this in mind. Now we do not construct this equation as an equation integral over p prime. Instead, we consider the minimal polynomial associated with y. So why we consider this a minimal polynomial instead of directly considering being integral over p prime will be clear in a minute. So instead we consider minimal polynomial of this y. So now we read our proposition 1 and make sense of this minimal polynomial. So the proposition 1 says that let E be extension of field of fractions k of a normal integral domain A if alpha in E is integral over A in A. So now we are considering, say, y in some extension field which is integral over, say, p prime, which we have just said it is integral over p prime in A. Then the minimal polynomial associated with alpha, in our case y, with coefficients in k. So this is the minimal polynomial associated with y, but the coefficients lie in k, which is the field of fractions of A, has coefficients in the radical of A. So A is p prime. So proposition 1 says that all these coefficients lie in the field of fractions of A. Then because of this proposition, so we are constructing minimal polynomial of y which will have its coefficients lying in the field of fractions of k, and then the proposition says that we can actually take down these field of fractions from k down to the radical of p prime. But this p prime is a prime ideal to begin with, so its radical is itself. So ai lies in p prime. So notice that we have not considered this directly as a monic polynomial to describe integral. We have gone about in a roundabout way because we wanted these coefficients to lie in field of fractions also. So now we come to the main result which we want to prove. So suppose B lies in A intersection P prime BQ, so that you can contract it back, say to an element B. Then we want to show that B also lies in P prime. So note that B inverse lies in K, so that we can get a minimal polynomial for S over K by setting y equals to Bs. So obviously B, we have shown that B lies in A intersection P prime BQ. So B lies in A, so B inverse will lie in the field of fractions of A, which is K. So we get a minimal polynomial for S over K. So we want to get a minimal polynomial for S over K by setting y equals to Bs here. So put y equals to Bs here. So we'll get Bs m plus a m minus 1 Bs m minus 1 and so on to a0 equals to 0. Now you divide throughout by Bm. So you will get Sm am minus 1 over b Sm minus 1 a0 over Bm all the way 0. So now again these coefficients lie in the field of fractions k. This again lies in the field of fractions k. And now we will use proposition 2. So let A be a normal integral domain, which we have, with field of fractions k. So consider a finite field extension this, an element alpha in E is integral over A. So now we have S instead of alpha, which is integral over A if and only if minimal polynomial of S has coefficients on A. So this minimal polynomial of S has coefficients in A. So these coefficients which we were considering in the field of fractions k, because of proposition 2 we can say they are in A. But we have already shown that this portion, this front part lies in P prime right here. So therefore or this front part lies in P prime. So these coefficients lie in P prime. So therefore this am minus I over bi also lies in P prime, because this entire thing is in A and the coefficient, this numerator is in P prime. So this is lying in P prime. So this is the crucial result, and from here we will show that B lies in P prime via contradiction. So you start with saying B does not lie in P prime. So this we are going to copy right here. So this implies S to the M lies within P prime of B, because now we can rewrite this equation like this: S of M is equal to minus am minus 1 by B times Sm minus 1 minus all the way to minus a0 by Pm. So all these things are in P prime because the coefficients are in P prime. So Sm lies in P prime. So P prime of B in particular. Yeah, so we can always extend this P prime to B, and then this lies within PB, which actually lies within Q, because we have seen that this ideal Q sits over P. So we had this ideal Q sitting over P. So if you extend this P here, you lie within Q. So this would imply that Sm lies within Q, but Q is a prime ideal, so S has to lie within Q. And this contradicts the definition of S, because by definition S comes from a multiplicatively closed set which sits in the complement of this prime ideal Q. So we have a contradiction. So it must be the case that our supposition is wrong. So B has to lie within P prime. And notice that this could be a point of confusion, that this is not an equation of y being integral over P prime. This is actually a minimal polynomial, because we wanted coefficients in K so that we can copy this down right here for S and then work with it. If to start with this is P prime, then it is very difficult to pass on here. So recall the theorem we have just proved. So say A is contained within B, both of them are integral domains, and A is normal, so it is integrally closed in its field of fractions, and B is integral over A. So consider this prime ideals. P prime is contained within P and both of them lie in A. P prime is contained within P and both of them lie in A. And let Q be a prime ideal of P which sits right over P. So that as you contract Q back to A, you get P. So Q intersection A is P. So then Q contains a prime ideal Q prime in B, such that if you contract back Q prime to A, you get P prime. So there exists such a Q prime. So you can always, you have a chain down here which is going down, because this containment is like this. You can construct a chain right on top of it. So let us do a corollary of this. So again, A is contained within B, both of them are integral domains. A is normal, P is integral over A. Consider this chain of prime ideals in A. P1 contains P2 all the way to Pn, and there is a chain of prime ideals in B. Q1 contains Q2 all the way to Qm. In particular, m is less than n. But each of these Qi's is sitting over Pi. So this Q1 is sitting over P1. You contract it back to A, you get P1. Q2 is sitting over P2. Qm is sitting over Pm. So now we can extend this chain all the way to n, because say if there is Pm plus 1 sitting here, you can always find Qm plus 1 sitting here by this theorem, and you can keep extending it till you get a chain like this. So this is called the going down theorem, because see, the ideals are contained within each other. So these two results are called going down theorem.